So yes, just as I mentioned, we will be going through the manual meshing in CENOS induction heating, and I will also try to make you perhaps make it understandable for users who have never seen this before. So first up, I would actually like to go through a small article on our website, which is about manual meshing in Salome, just for the ones of us who have never seen this before. So basically, what manual meshing and meshing in general is, it is taking our geometry, whatever kind of a geometry it would be, and splitting it all into smaller, some kind of triangles, because that's needed for the calculation part of the electromagnetics, the thermal analysis, everything. All of that depends on us splitting the geometry into simpler elements, which in this case would be the triangles. So here we can see some kind of a part which we have, and here you can see it all split into triangles. Yeah, also a couple of algorithms, and also about the skin layer. So to fight with the let's say skin effect that we have in induction heating, also what we will apply will be viscous layers on the surface of the mesh, so that we can be sure that the high current density at the beginning of our simulation will also nicely flow into the workpiece, and we won't lose anything there. Yeah, so we can turn back to the presentation. So in this presentation, I have prepared one kind of an example where you can see a part being meshed here on the top with some kind of a preset mesh max size value. So that's the size of these triangles, which you can see that everything is split into. And another example, which is with these triangles very fine. So the difference between these two will be that the one on the top has less of these mesh elements, so it will calculate faster. But the problem is that the thermal distribution and the temperature on this workpiece might also travel travel visibly through these triangles. So the one on the bottom is with a lot more elements, so it will calculate a lot slower, but it has the more elements, so you'll see the temperature distribution a lot better in the end results. What we will try to achieve today is to actually get the best of both of these kind of approaches. So having a very rough kind of a mesh or having a very fine mesh. And that would be that we have a mesh which is rough on the places where the inductor is not that close to the workpiece, and finer where we will have very high current density. And well, yeah, for this application, there's also hardening happening at this location. So yeah, so to put it simply, then we have rougher mesh everywhere else and finer where we really need it, not on the entire workpiece, but only on specific places. What are the positives with this manual mesh optimization? So yeah, once again, the mesh max sizes will be better optimized. That means we will have faster calculations, but they will still be accurate. So yeah, better temperature tracking. Also, the reduced mesh size. So instead of having the very small mesh triangles on the whole workpiece, but instead having them only on certain places, will result in faster running calculations. Another good thing here is that more complex CAD can be used, and perhaps even less need for CAD simplification. Because if you spend a bit more time meshing, and you try to understand what kind of values would suit the particular project best, you can also get away with having some kind of a CAD which is a lot less simplified than for the some kind of automatic meshing that we would need to simplify the CAD files a lot more. Yes, what kinds of negatives, let's say, with this approach? So manual meshing does require more time spent with setting up the case, because we have to also enter Salome, which is where we deal with the manual meshing as of right now. And of course, it does require a bit of training to understand this approach a little bit better. That's also something which I will try to show you today, and let's hope that we get through this and understand this approach better at the end of this webinar. But okay, let's start with setting up the case. So yeah, first up, as always, what we do, we go to Save As and just save the case. Go over here and I will write down the name of it, CENOS webinar, in this case, webinar 3. Press save, and the approach which we will actually use in this case will be the FromCAD approach. So we will deal with the whole geometry grouping in FromCAD and then with the meshing in the advanced geometry editor. Yeah, so here, let's enter the FromCAD, and for this I have my step files already made right here. So I just click on them, press open, and the CAD files will be processed. Okay, yeah, so here you can see the geometry which we'll be working with. In this case, it's actually a slice geometry of a large gear hardening. And here we have our little inductor also with the flux concentrator in this case. So it's a teeth by teeth kind of application. For the simplicity of this video, I won't be like having the proper boundary conditions for the sides here to set it up as a slice. For that, you can check our previous webinar recording. But I will mainly focus on what we need for manual meshing. In this case, I will also create the automatic air domain. Press yes, select the inductor's terminals. So here is the entry and here is the exit. Press create air. Air will be created in a moment. And I will start with the groups, which would be made as we would usually have them. So first, I will select the workpiece as we would usually do it. So here for the workpiece solid, press select it here on the left, write in its name here to be the workpiece, assign workpiece. In the same way for the inductor, we just click on it, click on the inductor, rename it. And in this case, since we also have the flux concentrator, I will press add new role and choose the flux concentrator, which is right over here. Flux concentrator. Okay, assign it. And right now we will have some kind of changes from the usual case setup. So actually what we'll need will be two separate workpiece surfaces. So in this case, I will have one workpiece surface for this gap here where I will want the mesh to be finer, and a separate workpiece surface for all of the other faces, because we still need to have some kind of heat loss happening on the entire workpiece, of course. Nobody has canceled all of that. So yeah, so for this workpiece surface, I will press select. And here, what you would do also for your cases, you would select the faces where you would like the mesh to be finer. So as I said, in this case, those would be this one, the one in the middle, and this face right over here. Yeah, by holding down Shift, you can select multiple of them. Yeah, so these would be these three faces. If you want, you can also have the ones on the sides. Also, if you would like to let's say have multiple of these groups where you have these specific faces where you want different mesh size, you can also create as many of these groups as you want. You can actually have a different mesh size for each of the faces if you want. But yeah, I will press assign workpiece surface, and right now to assign the rest of the workpiece surface, I will just press add new role, check the workpiece surface here, and I will filter the faces by volume. Just select the workpiece so we can select them easier. And I can press select all, but only scroll a bit down and deselect the workpiece surface which we have already, because that one we don't need in this group. Press assign. And for this, for the setup, at least for this case, this is pretty much it. One thing which I can mention, I will also mention it a bit later, but also if you would like to have some kind of inductor phases be finer, so in this case, let's say if this inductor phase we would like to have finer, we can add new role, other, and then just select those phases also in a separate group. All right, now we can go through the physics. In the physics, I will input some kind of generic values because we will mainly focus on the mesh in just a moment. In the simulation control, I will input frequency of 10,000 hertz and time of, let's say, 5 seconds, calculation time step of 0.1. And then actually for motion, if you would like to also recreate this case after the recording is uploaded to YouTube, we can also have some kind of a complex motion. In this case, that would be the z-axis, and the inductor would move downwards, or the workpiece would move upwards. In this case, I will actually move the workpiece with some kind of a movement speed here on the y-axis of, let's say, something like this. So that's half of, that's a little maybe, okay, something like this in the upward direction to the z-axis. For the flux concentrator, we just have to select the material. In this case, I will use Ferrotron 559H. Now, nothing more to do here unless you want to change the magnetic permeability and run it with a set magnetic permeability. For the inductor, I will input the current which we will use, which will be, let's say, 5,000 amps. And for the workpiece, I will input the material of 1045 medium carbon steel. And here for the boundary conditions, so actually we have two of them, of course, since we have two of these workpiece surface groups. But I will actually input exactly the same parameters for both of them. So no cooling, and since the material is the same, the emissivity is the same, and the emissivity is 0.8. Also for these phases, also the same thing. Another thing which I can mention, so if you also make multiple groups, you can of course also have different cooling coefficients for multiple phases. So in this case, perhaps these gaps over here would receive a different kind of cooling than the rest of the workpiece. But all right, now we will get to the main course, which will be going back to the geometry, entering the mesh options, and pressing create automatic mesh now. So what this will do, it will create the automatic mesh. If you have ever run a FromCAD case without having manual mesh adjustment, it will just make the automatic mesh already. So this is with some kind of presets that the software has, and we will use this automatic mesh in Salome just to adjust its values. So it will basically will have created a template for us, which we will be very nicely able to use. And for this template, we will just adjust the max size values in a way that we see fit. Yeah, this might take a moment. Oh, actually, it computed quicker than I thought. Also here on the bottom right, for some of you which might have not seen this before, we can also see the number of mesh elements, so number of triangles that we have produced, so for the air, for the flux, inductor, workpiece, and total. But as I said, what we will actually do, we will open the advanced geometry editor and adjust the mesh max size values on our own. Okay, Salome is opening in just a moment. So yeah, while we do not send the mesh back from Salome, this window will be opened all the time in CENOS. So that will only end when the mesh will be received. Yeah, so Salome has opened for me, and since we have dealt with the geometry and the grouping through FromCAD, we can automatically go to the very last section here, which is the mesh. In the meshing section, here on the left, we can see the object browser. So here for the mesh, we can click the open button, and here we can see our mesh 1. So mesh 1 is the large general mesh inside of which all of our smaller solids are located. But inside of this submesh, we also this mesh we have submeshes, which are our solids. So the board piece, inductor, and flux concentrator. Once again, as I said, this is pretty much as a template that CENOS has made, and we can very nicely adjust these mesh size triangle values for each of these separate submeshes. What I will do, I will right-click on mesh 1 and just try to compute the mesh. I'm not sure if it will go through or not. We will be able to see. But we will, after it does compute or it doesn't compute, we will have a good idea of how the mesh looks like now, what can also be adjusted, or perhaps yeah, any kind of changes that might need to be done. Perhaps don't be afraid of all of the buttons which are here on the top, because actually in the meshing section we only use the ones which is create mesh or create sub mesh. The rest of them we just right click on mesh 1, and these things are not necessary. Yeah, another thing which I can mention, if sometimes you also see that this meshing, this computing is taking a lot of time, have a thought: is your geometry really that complex that it should take that much time? Maybe it has it has stuck at some point. I would say if it doesn't compute for like 5 minutes, then and your geometry is not very complex, then I would think that it has most likely stopped or is just not able to compute something. Okay, for us, luckily the mesh computation has succeeded, and right here some of the interesting things which we can see. Here, where we have the volumes, this amount tells us how many triangles we have actually made. So how many mesh objects have been made in this mesh. Couple of quick tips which I can tell you about this number. I would usually recommend that you try to keep it under 300,000. That's for well, yeah, depending on how complex your case is, but for most cases, you should be able to keep it under 300,000. Why do we want to keep the amount under 300,000? Is because afterwards the amount of RAM that's necessary for computing the case, it just starts to grow quite a bit. If you have 32 gigabytes of RAM, you should be able to compute cases up to like 450,000 elements. But yeah, then upwards more and more RAM is required. Some other things which we can see here. So actually, these two things are some kind of warnings. Actually, they're not an error, but they are a warning, which tells us that some kind of thickness for mesh for the viscous layers has not been reached. This can be because of the geometry being, let's say, too thin, or having some kind of other issues where some kind of mesh values which the automatic mesh has input cannot be reached. So it just tells us that. But this does not mean that there's some kind of an actual issue, because there's no real errors, just some warnings. If we close this up, we can finally take a look at the mesh. So here we can see the large airbox. So this is the entire airbox. You can also see that the triangles here are quite large. And here outwards of the airbox, if we zoom in, we can actually see the inductors terminals with actually the viscous layers already developed on the sides of the, on all of the outer faces of the inductor. If I disable visibility for mesh 1 and just enable it for each of the submeshes, here we can see our flux concentrator. Here we can see our inductor as well. So we can see everything has nicely split into triangles. It looks quite good, to be honest. and also our workpiece, which, if you ask me, is a little too rough for what we would like to see. Basically, if we would run the case like this, we would most likely also see that there are some hotspots which are resulted by the mesh, because they're just too little of too few of the points where the simulation can compute and result in some kind of nice temperature distribution. So you will probably see these triangles also in the result. Yeah, but okay, what we will do now, we will try to adjust this triangle size just for the workpiece, let's say. So to do that, we click on solid one, right click on it, press edit submesh, and when we enter here, we are automatically in the 3D section. Here we can adjust the viscous layers. So that's exactly the same thing which we saw on the inductor. We actually have them also inside of the workpiece, as well as a couple of computational algorithms in the 2D section. And for the 1D section, here we can actually adjust the max size of the triangles, which we have on the within our workpiece. To adjust this value, we can click here on the gear icon and just press max size. So this will make a new some kind of like new kind of value for the mesh for the max size of the triangle's edges. Or we can press the edit button to edit the value which we already have. So how this works is, as you can see, the length here is like 2. The units are millimeters, I believe. So 2 millimeters. And what we can do, if we like decrease this value, the triangles will also get smaller. Since their edges won't be able to be as long as they used to be. If I write in the value of 1, so this is 2 times smaller, press OK, apply and close, and I will try to recompute the workpiece. Here I will click on mesh 1, right click, and clear the mesh data, just so we don't have this old workpiece and the old mesh on top of it, since we changed the value here in the submesh 1. Right click on submesh solid 1 and try to compute the mesh. We will see how long this takes, but basically it should be a bit longer than at least previously the workpiece submesh computed, because, as I said, we will have 2 times smaller triangles. So this means, generally speaking, like roughly, I guess, well, okay, it's tough to say how much exactly, but also more of the smaller triangles, since we still have to fill the same volume, just with less triangles. In this case, I expect that it should also take a moment, because we still didn't adjust the viscous layer values, which is also something very, very useful that we could do. Okay, I will try to cancel this. We will see what has already been made. Then we will adjust the viscous layer values and try to recompute it again. Just to show you also how much the viscous layers values can also change the change how quickly the case computes. About viscous layers, so yeah, I mentioned at the very beginning of the video. So here we have the multiple elements on the very surface of the workpiece. The small problem there is that in the original originally computed values by the software, there's a bit too much of these viscous layers, at least for most cases. So that's also something which we will reduce in order to have less elements in the end. Yeah, here we can see that the mesh computation has failed. Now this is an actual error, but that's all because I actually stopped it. We can actually see that on the surface, these elements have already computed, and we can see that the mesh is actually like quite a lot better than it used to be. This is like pretty much something actually usable already. But yeah, then to adjust the viscous layers values, we will go to submesh solid 1, press edit submesh, and go for the viscous layers here to edit their values. If I press edit, we can see the three main things which we have for the viscous layers. So the thickness, that is how thick the viscous layers will be, the number of layers, so this is how many of these layers there will be, and the stretch factor, which is by how much each of the next layers is thicker than the previous one. So what I would like to comment here, number of layers 17, for usual kind of cases, this is way too much. I would say if you're running low frequency, then usually number of layers 4 is perfectly okay. And then as you start to increase the frequency, or your case starts to get more complex, I would suggest, if possible, have 5 or 6 layers. And if you have really high frequencies, then have like 8 as the number of layers at least. For this case, I will use 5 as my number of layers, and for the total thickness, this value has been computed to match the 17 viscous layers. So this thickness value also has to be recomputed. To recompute this, some of you who were here for the 2D manual meshing and case setup video, you will know that we use the viscous layers calculator, which I have right over here. And some of the inputs which we have here at the very top is the magnetic permeability of the material, the frequency we're running, and the maximum electric conductivity. And then at the end we get the recommended viscous layers skin depth values. So here we can also see common magnetic permeability values and common electric conductivity values. As it was 1045 steel that I used for the workpiece, we can check the common move values. This is once again an approximation, but it's something which works quite well. So 150, we just input that right over here. After I press enter, you will already see how these values change here on the right. Yeah, so you can see that they greatly change just by changing the magnetic permeability. Then the frequency, it is 10 kilohertz, that's correct. And the electric conductivity should be changed for the one which I have here for the 1045 medium carbon steel. Right here we can see if our number of layers is 5, so that's the number of layers that we do run. We have to use the skin depth of 0.35 roughly in millimeters. So let's just go back to Salome and input that value. So here 0.35. And that's pretty much it. Nothing else needs to be changed. Press OK. And that's the only thing which we will change. I will press apply and close. Once again, clear the mesh data just so we don't have any leftovers. And I will press compute, and I believe this will run through a lot quicker than it did previously. So previously we actually canceled the computation of the mesh, but right here I think that it will manage to go through. Yeah, so as I said, it manages to go through and a lot quicker than it did previously. Perhaps to put a better visualization on how these viscous layers actually look, what I can do, I can right click on our workpiece, use the clipping aspect right here, and what this will allow is to actually see what's happening on the inside of the workpiece. Here on the top, I can select new, some absolute or relative. Let's go for absolute. And here we can see where our cut is located. So we can move it kind of like this by dragging the arrow or dragging the red box. Yeah, so we can kind of see where we want the cut to be made. For me, it's perfectly okay to have it here. Press apply and close, and we can see how this mesh actually looks like also on the inside of the workpiece. So here we can see the general mesh triangles, and on the very surface, on all the parts which we cut, we can see also how our viscous layers are looking. In the next webinar, which will be the fourth one about the result visualization, we will also see how much these actually do impact the current density and the proper soaking up of the current inside of the workpiece. But okay, this is it for the initial adjustments for the workpiece submesh. In the same way, we can go for the inductor submesh, which I believe was this one, or this was just a moment. Oh no, never mind. That was the flux. Let's go for this submesh, which should be the inductor. Yeah, and here we can see some kind of viscous layers values have not been reached, but we will change those in just a moment. So yeah, about the max size, so the total size of the inductor triangles. In this case, I think it is okay to run it like this, but I would usually also try to have the inductor a bit rougher. So that would mean a general rule of thumb is that on any kind of like side planes that you have, that you would have at least 2 to 3 mesh elements from one side to the other. So here we can see 2 to 3, but here on the top we have a bit more. But for this case, it's okay. The only thing which we will adjust will be the viscous layers, which we can see here. And if I press edit the submesh, drag it to the left. Here in 3D section, once again, we have the viscous layers. If I press edit, we can see that the number of layers is 7. So here, if we actually count them one by one, it should be 1, 2, 3, 4, 5, 6, 7. So that's exactly how much we have. For this application, since it's quite low frequency, I will actually use number of layers as 4, and the total thickness we can very conveniently just check in our calculator. For the inductor, so everything is preset. We just have to check the value, and the recommended skin depth is 1.3 millimeters, roughly. So we can also adjust that. It's okay, and apply and close. One thing which has just appeared, the software is asking us is telling us that there are two submeshes which are closely together to one another. So in this case, it's the flux and the inductor, which is directly on top of each other. So it's asking which one of these two we should compute first. Yeah, we can press yes, and here we have to select which one to compute first. So actually, in this case, solid 2, that's the inductor, and solid 3, that's the flux. So we should have the inductor actually be higher than the flux. If these are switched in your case, then you can just click these arrows and change their submesh priority. Yeah, press apply and close. We can clear the mesh data once again and just compute our inductor to see how it's doing. So yeah, once again, we have that warning for the viscous layers, which is most likely because of our geometry being quite thin. So these viscous layers cannot develop as large as they would like to. But still, we can see that now we have 1, 2, 3, 4 layers instead of 7. Which is once again a bit of an optimization, because if we imagine each of these triangles that you see on the surface, if they previously had 7 elements underneath and now they have just 4, that's also something which just adds up in the end, and we come out with a lot of a more optimized mesh. For the flux, something which I can also mention if we compute the flux. In this case, the flux is quite a bit too fine, I would say. Similarly, as for the inductor, we can make it quite a bit rougher, and the results pretty much won't change that much for the workpiece heating. If, of course, you're interested in the flux heating or the magnetic flux density in the flux, as well as the current density in the inductor, then of course have the inductor as fine as you need it to be. Now, what we will be doing, we will be making we will be making a mesh which is finer in a certain place on our workpiece. So for this, I will recompute the workpiece, and then we will also implement the finer mesh in the very gap, so we don't have to make the entire workpiece a lot finer. Yeah. Actually, one question has appeared in the chat box about the possibility to implement skin layers only on some kind of surfaces in the workpiece instead of the entire workpiece. This is something which we can also touch up on very quickly. We will actually go through the workpiece spine, which I would like to show you now, and then I can also show you the implementation of viscous layers on only specific faces, which also can be used. That's a bit of an advanced tactic, but yeah, I will keep that in mind. Okay, so right now to have the mesh only finer here in this gap. What we actually will need to do, we will need to quickly go to the geometry part to check which of the objects in our group that we made in FromCAD is actually the faces which we want to make fine. Yeah, I'll try to put it maybe a bit more simply. So here, if you go to geometry, here on the left, in the object browser, similarly as we did for the workpiece, if we open it up and go down, here in the partition, we can see all of the geometry groups that we made in FromCAD. So here we have solid 3, solid 2, solid 1, which are our solids, as well as some kind of faces. So here we have merged face 18. So this is actually the rest of our workpiece interface. And then the merged face 6, which is the one which we would actually like to have finer. So right now, since we know that this is the face which we need to make finer, what we can do, we can go back to the mesh and create a separate submesh with smaller triangles only for this geometrical object. To do that, we will go back to the meshing. I will click on mesh 1, right-click on it, create a submesh. And for the submesh name, I will write in workpiece fine, let's say. And the geometry, we just select the one which we just saw, that is the right one. So that's merged face 6. I click on it. Right now, what we need to do is assign set of hypotheses to the automatic triangulation. And here we can actually input the max size, which we also did for the workpiece. So the max size here, since for the workpiece we had it as 1 millimeter, and we need this to be smaller, so the mesh is finer, I will actually try a value of 0.6, let's say, and we will see what happens. Also, yeah, just to organize it better, also input that name there, press OK. And one thing to mention, here for the algorithm, you can change it to NetGen 2D, as well as include the length from edges hypothesis, just to have a better element count economy. Yeah, this is just changing the algorithm, so it's a little bit more, with a bit less elements in the end. We can press apply and close, and right now, similarly as we did before, the software is asking us which one of these submeshes, which is right on top of each other, so the workpiece fine and the workpiece, should we compute first. We click yes here, and here for the order of submeshing, we actually need the workpiece fine to be higher than our workpiece 1 solid. So we click on it, click the arrow button, and right now we will first compute the workpiece fine and then only the rest of the workpiece solid. So this is how it should be. Press apply and close, then we can clear the mesh data, compute the workpiece fine to have a look at it. Yeah, so it has computed, no errors. We can kind of not see maybe that much that it's a bit finer than the rest of the workpiece, at least right now. But we can compute the workpiece so that we can see the difference perhaps a little bit better. If we won't see it that much, then I will just make the workpiece rougher as it originally was, because actually if we make this local adjustment, then we don't need the rest of the workpiece to be as fine as I had it just now. But yeah, mesh computation has succeeded, and we can we can kind of see the difference if we take a look at this gap and the difference and the mesh sizes at this gap. So here there's a lot more triangles than this gap or this gap right over here. Also on the top we can see that the mesh is like there's smaller triangles here than there are at these edges for the ones at the side. Something which Raymond has asked us in the chat is if we can also like tell the software to have only viscous layers on specific faces instead of having them on the entire workpiece. In this case, I would say it's best to have the viscous layer pretty much everywhere. That would be just to make sure that we don't have any issues. But actually these faces on the sides, so this face, let's say this face in the back and this face on the side, it actually doesn't need viscous layers, as the magnetic field and the current density will be high right around here, not at the end or at the sides here. So what we actually could do, we can go quickly to the geometry. I will kind of include this with another thing which I wanted to show you. So to not have viscous layers on certain faces, we actually also have to tell the software which of these faces we wouldn't like the viscous layers to be on. To do that, we perhaps should have done that already when we were setting up everything in FromCAD. But if you didn't do it then, no worries. You can actually also do it here in the geometry section. For the partition 1, we can right-click on it and create a new group, exactly the same way as we did for 2D case setup. So here we can create group. On the top, we can select what kind of group. So in this case, it will be faces, because I want to apply some kind of faces where I don't want the viscous layers to be. To get to those faces, I have to click on the airbox here. So hold down Shift to select multiple and hide it, just so we can see what's happening on the inside. Similarly for all of the rest of them. Right now, to select these faces where I perhaps don't want the viscous layers to be, I just click on one of them, the other one, and the third one. Press add, and all three of these faces are in this group. I will name this group as let's say geometry, since we made it in geometry, and let's say no viscous layers workpiece, something like this. Applying close, and right now we have that group actually here on the bottom. Yeah, so we can already see how it looks like. To implement this group, we go back to the mesh, and right now pay close attention to how our workpiece sides are looking right now. So basically what we have is that we have the viscous layers on all of the faces, so we can't actually see them because they're all on the inside. What I will do now, I will open these faces up, so we will actually be able to see the viscous layers that are in this face, in the face on the bottom, and also the ones on the sides. So yeah, so to do that, we can click on the mesh, submesh solid 1. So this is the workpiece. Right-click on it, edit the submesh, and here for the viscous layers, we go to edit them once again. And here on the bottom, we can tell the software the faces that we want to have with viscous layers or faces without the viscous layers. So that's the one which we will actually use. So faces without viscous layers, here on the left, we just click on the group which we just made, press add, and press OK. Similar way to remove it. Okay, applying close, and right now I will just clear the mesh data and recompute the workpiece once again, and you will be able to see the changes. About this approach, I would say first get the workpiece fine ready, get the mesh max sizes ready, get the viscous layer ready, and then only if you are if you think that is the best way to go, then you can try this approach also to save a bit on the element count economy. Right here, what you can actually see is the negative thing of this is that there's some kind of an actual error which we previously didn't have. So the error is that because we took out some kind of some faces away from the viscous layers, basically the balance inside of the workpiece has sort of shifted. So there's like some faces have it, some faces don't, and some kind of places, as like this place, it's actually okay. We can see the viscous layer. There's no kind of issues that go on further into the workpiece. But here on the bottom, not on the bottom, but at the other end, we can see that the viscous layers at this edge are sort of like colliding and like shifting together here, and that's making this error most likely. Actually, if we would try, yeah, we can also see some kind of a red line that has appeared here. Actually, in this case, we might have gotten away with it if we didn't take the face that's on the other end here. But as I said, this is exactly what I wanted to tell you, that you have to be cautious with this approach. Yeah, so in this case, in order to get everything running again, I just go to Solid 1, Edit, and actually I can just remove these faces out and everything will work again. Another thing which we can try to do, we can try to get only this one face out, if we can find it. So this is actually 24. If we can see how it highlights, so face number 4 is this one, face 24 is this one, and face 14 is this one. So what we can try to do, we can click on face 24, so this is the middle one, remove it out of this option, try to apply and close, clear the image data once again, and we can see if this time we will have an error or not. Once again, this is more advanced. This is getting into some more advanced features which we can use. As I said, if it's not necessary, if you're not sure about this, I'm quite sure that your case will run okay, even if you have the viscous layers everywhere. So it's not something that's necessary to be done. Also, in the same way, of course, this applies to the inductor. Also, if you want some kind of places on the inductor where you don't need the viscous layers, you can also do that. Yeah, actually, in this case, so as I thought, the problematic face was this one on the very bottom. As we removed it from that, from assigning there, we can see that there's no more errors. If we close it up, we can see that everything now works fluently. No more, we don't have these weird things here on the at the edges, and everything should be fine. And we have saved a bit of elements. Yeah. What else I wanted to show you? Oh, yeah. No worries. As I said, if possible, that's something to use if you feel comfortable with it. What I will do right now, I will click on mesh 1, recompute it. We will see how long this takes. But another thing which I want you to understand is that this whole mesh, it's like a connected kind of thing. So everything inside of it, like inductor, let's say, workpiece, everything still is connected together by some kind of triangle. So if, let's say also, if one of the elements is very fine, the triangles from that very fine element still have to develop and then go on to the other elements which are less fine. Yeah, to better visualize this, I will try to compute the mesh and clip it open so you can perhaps better understand what I mean. Another thing which is sometimes very useful to do, here where we made that group for the geometry no viscous layers, so you can actually also make a group with some lines. And you can make a submesh for lines that would make like places, let's say, as right here. So this top line, this like middle bit, and then the rest of it, that would make the mesh at those lines finer. So that's also something to do. That's also sometimes quite useful. So yeah, here we can see our mesh computation has succeeded. We have a bit more volumes that we had at the beginning, but we have a lot finer mesh than we had in the beginning. So this is a lot better for the temperature distribution. Once again, to further decrease this value, we can make the rest of the workpiece submesh a bit rougher by adjusting the submesh solid 1 max size, increase it back to 2 as we had originally. Right now, to see inside of the mesh, I will flip it once again to show you perhaps to give the understanding of how everything is connected together. So yes, something like this. This should work fine. Applying close. Yeah, so here from the side, we can see how the mesh is kind of connected together. So on the very outside, we have very large mesh triangles. That's for the mesh 1. That's where the airbox is. We don't really need the very fine elements there. But you can see as everything like approaches the smaller elements, these triangles also start to get smaller. So yeah, and similarly also over here nearby the inductor, you can see that the air elements are also quite a lot smaller. So everything kind of has an impact on each other. So that's also something to keep in mind. If you have geometry imported here, which is some kind of problematic geometry with small details, things like that, you can imagine if the large airbox tries to gap into these smaller details, that causes the problems. So once again, you can see it on our documentation page. If possible, either get rid of the small details if they're not like critical to your design, or make these like small details also with a very fine mesh, similarly as we did here, and maybe the mesh will be okay and will go through. For the last step, which I have intended, as I see we have taken quite a bit of time. So the last thing that you should know how to do after you compute everything, so you would clear the mesh data and recompute the mesh. So once your mesh is perfectly okay, you click mesh 1, go to tools, plugins, and send the entire mesh back to CENOS. Yeah, so here you have to also select the groups that you want to send to CENOS. Basically, these are all the groups that you made in FromCAD. The only change here is that one group which I made in Salome. So the group, this one, geometry, no viscous layers workpiece. So that's a face group which I made in Salome. You do not need to send this back to CENOS. Because we only used it to play around with the mesh. Further in the physics section, we do not need that group. So yeah, we can just press send mesh to CENOS, and let's hope that everything works. I do not expect any kind of problems with it. So yeah, here we can see that the mesh is writing actually. So in this case, we don't have any kind of issues. But a good point which Raymond has just written down in the chat is, can we check the mesh quality at this stage? As well as sometimes taper elements appear while exporting mesh to CENOS, but can we check it beforehand? That's a good question. We can actually do that. I will perhaps then open our documentation page to understand what we are talking about for the ones who do not know. So here for the aspect ratio or the taper, taper is something which applies to the 2D cases, which is, well, mostly to the 2D cases, which is wherever we have some kind of like elements which sort of don't fit in the whole process. So for taper, it's some kind of elements in triangles where the taper value is above 0.5. And for the aspect ratio, this means that some kind of triangle elements are with such of a high aspect ratio from one side to the other, that pretty much these triangles are like faces. They're so thin that they're pretty much faces, and that is not something which we want to have. So you might see errors like this also in the advanced geometry editor, And to battle them, you can like decrease the max size or play around with the viscous layers values. So here you will actually see a nice group underneath the underneath our groups of faces or groups of volumes with aspect ratio error elements. So that's where you will understand where exactly these elements are from. To check if our aspect ratio is okay and we don't have some kind of very high aspect ratio elements beforehand, what we can do, we click on mesh 1, we go to controls, and we can have face controls, and here we have taper, which is exactly what Raymond was asking about, or more likely for 3D cases, we have the volume controls, and here we can see aspect ratio 3D. So let me enable it. We will see how nicely it visualizes. Okay, so yeah, it didn't visualize as colorfully as I imagined, but basically here on the bottom, we can now see the maximum aspect ratio value. So that's like how kind of thin the triangles are, and the minimum. The maximum one, that's at some kind of a point inside of the mesh. We do not want this to exceed 10,000. I would personally recommend don't have it more than 5,000 if possible, because if it's that high, that already like implies that there might be some kind of issue. If we zoom in, we might be able to find some of these elements, maybe in the viscous layers. Actually, it looks like we might not be able to find them, but generally in a standard kind of a case, if you zoom in to viscous layers, if your geometry is not bad or problematic, you should see these red lines, this redder part in the viscous layers or somewhere like that. If your geometry is problematic, you will see these in the places that are problematic. Yeah, but this is some kind of a like first test which we can do with the mesh to yeah, to understand how large our aspect ratio is before we send it back to CENOS. There's actually another nice way to filter the aspect ratio elements. Let's say all of the elements above aspect ratio of 400. But actually, I have a bit forgotten of how exactly that was done, but I believe that should be visible also in the documentation page. Yeah. Yeah, but actually at this point, since the mesh has been sent to CENOS, and more or less this is it for what I wanted to explain. You can also ask any kind of questions which you might have gathered. Yep, no worries. I actually wanted to talk a bit more about the some kind of other things as well, but I hope I covered more or less the most common issues which we encounter. Yeah, well, some questions appear. Once again, just to show you in our documentation page, all of the problems, well, most of the problems which you will encounter in meshing, especially the ones which are critical errors, those directly those are directly connected to your CAD. If your CAD has some kind of issues, if your geometry is not as simplified as it could be, so yeah, that's kind of what to look out for. That's also what we try to tell you, that these kind of issues, they will appear in the meshing. One quick tip which I can tell you, if you're experiencing these aspect ratio errors and you don't know exactly where your issues on the mesh could be, one thing to try for that, if you at least understand from which solid the issues might be coming from, you can go in that solid submesh, right click, edit submesh, and here in the 2D section, you can disable length from edges. So this will length from edges, what it allows actually is for more bad or complex CAD to be kind of made in a bit of a more simplistic kind of a way that allows the meshing to go through. But if you disable it and also enable the triangle Mephisto as the algorithm, it will take a bit more time to compute. But on the mesh afterwards, you might see a place where, let's say, the mesh is going as expected, so the triangles are the same, and then some kind of a point where you see very, very small triangle. So that's, at least from my personal experience, that's most likely where some kind of issues will be. That's some kind of way how to actually troubleshoot the geometry also without yeah, if you with the mesh, if you're not sure where the issue could be. Okay, I see no questions as of right now. So what else could I tell you? There's actually loads of things that I wanted to tell in this webinar, but I'm just trying to compress everything, as quickly as possible. But yeah, I think I have covered most of it. If there's no more questions, then that's pretty much it from my side. Once again, if you encounter any issues here, you can reach out to the support live chat. We can have a look at the geometry, perhaps we can figure out where the issue is. But yeah, thank you for attending then. And if there's no more questions, then yeah, good luck on your project.